broadcast is now starting. All attendees are in listen-only mode.
Hi, everyone, and welcome to the Better Buildings Alliance Plug and Process Loads team webinar. I'm Kim Trenbath from the National Renewable Energy Laboratory, and I will be leading the discussion today. I'm going to jump right into it because we have a packed agenda, and I want to thank, next slide, please. I also want to thank all those who are in attendance today, and I want to thank our presenters and my greater team for putting this webinar together. So our exciting agenda includes our PPL team updates, and then we have two technical presentations. Ms. Amanda Farthing is going to be speaking about zero client computing, and Ms. Jen Amen is going to be speaking about driving down consumer electronics energy use. We've got a packed agenda, like I said, so we might have a little bit of time for some Q&A and discussion and member updates at the end. Next slide. I just wanted to introduce the team players for the Plug and Process Loads technical research team. I'm the technical lead. You can reach me at my email that you see posted. And also from NREL is Bennett Doherty, and our team members also include our Waypoint Energy colleagues, Katie Vrabel and Carly Burke. So we all work together as a team, so please feel free to respond to any of us if you have any questions about the PPL technical research team. Next slide. I'm going to go into the first part of the agenda. We're going to talk about some of the publications that our team has recently released. The most recent one is a journal article on energy in buildings, a journal article from Energy in Buildings written by myself and Bennett Doherty. It was published in October, and this is titled Device Level Plug Load Disaggregation in a Zero Energy Office Building and Opportunities for Energy Savings. In this research, we developed a method to disaggregate plug loads using a limited number of plug load metering devices and the building plug load submeter. And this model was effective in predicting the shape of the building's average plug loads, but it didn't account for the entire magnitude of the load. And we also found some interesting things about the plug load load shape. We found that a lot of the devices that were contributing to the unoccupied loads, they included audio-visual equipment. We found that the plug load power consumption is highly correlated with the laptop and monitor power consumption in the building, as it is an office building. And we had a peak at noon, and we found that the microwaves contributed to the peak at noon. Next slide. Actually, can we go back to the previous slide? I forgot to say one more thing. So when we send this PDF out to the team later today, you'll have a link to be able to download this journal article from Energy in Buildings for free, but that link will expire in December. So it's a free download for now. Next slide, please. Another publication I want to highlight is we released as a technical report our integrating smart PPL controls into EMIS platforms landscaping study. This was authored by myself and Rose Langner, and this work really outlined a lot of the work that we completed in fiscal year 19 and we're still working on in fiscal year 20 and beyond. Next slide. That landscaping study led us to working on the following publication, Emerging Technologies for Improved Plug Load Management Systems. And those emerging technologies include learning behavior algorithms and automatic and dynamic load detection. This work is going to be published as an NREL technical report in the next few months, and the authors include Bennett Doherty, myself, and our Waypoint colleagues, Katie Vrabel and Carly Burke. Next slide, please. So building off of the emerging technologies report, we're taking some of the research that we did in that report and bringing it into the laboratory setting. We're looking at automatic and dynamic load detection in the lab, and these technologies would work with a plug load management system or one of those smart outlets, and would allow the plug load management system to automatically detect what load is plugged in and where the location of that load is located in an explicit manner. So we're working on some proof of concept work in the laboratory this first half of the fiscal year. And then the second project that we're working on is interoperability of plug load controls with other building systems into EMIS platforms. A lot of the national labs right now are focusing on interoperability, trying to focus on how we can have all these different building management systems interact with each other and interoperate with each other. And so this work will correspond with the work that a lot of the other labs and NREL are currently working on. Next slide, please. So you might have heard of the Interior Lighting Campaign. It is run by the Pacific Northwest National Lab, or PNNL. That lighting campaign is now the Integrated Lighting Campaign, and it is now focusing on integration of other building and use systems with the plug load lighting, or not the plug load, sorry, the lighting controls. So I just wanted to say that if you're interested in, if you are interested or if you are currently integrating your plug loads with your lighting controls, please let us know. You can contact the lead from PNNL, Felipe Leon, at this email that you see here. And the other thing that will be available is you'll be able to apply for recognition through the campaign in one of these new integrated and innovative categories. So be sure to submit your application to the ILC. Next slide, please. Now we're moving on to some upcoming events. I wanted to highlight all the Better Buildings webinars that are available. Some of them are available online now because they were pre-recorded, and some of them are upcoming, so be sure to register for these. Next slide, please. Another upcoming item is that the GSA and DOE request for information on grid interactive efficient buildings is going to close on December 9th. So we are looking for technologies that will help improve buildings grid interactivity and efficiency. And so there was a recorded webinar that's available from this link here. It was a couple weeks ago. And also the RFI is currently posted and you can access it from the link. So technologies that are interested in applying or submitting their information should do this by December 9th. Next slide. I also want to highlight an upcoming event from the Smart Energy Analytics campaign. They have a webinar on November 20th, and in this webinar, they will be presenting on the 2019 New Installation Recognition Awards. And here's the link to register. Smart Energy Analytics is important because they can connect to the EMISs, and as we're working on improved interoperability between plug load management systems and EMISs, this is a great way to take a step forward in that full building integration. Next slide, please. And finally, I want to highlight the Better Buildings 2020 Summit. This is going to be on June 8th through 10th in Arlington, Virginia at the Hyatt Regency in Crystal City. The registration opens in January, and there's more information on the link. And with that, that's all the initial announcements that we have from the Plug and Process Load technical team. I'm excited to get into the technical presentations. So what I'm going to do now is I'm going to move to the next slide and introduce our first guest speaker. Ms. Amanda Farthing is our first guest speaker. She's going to be speaking on zero energy clients in office buildings. Ms. Farthing is a master's student at the University of Michigan pursuing a dual degree in mechanical engineering and sustainable systems. Her studies and research focuses on clean energy development, particularly at the city scale. Ms. Farthing previously worked with the Commercial Buildings Research Group at NREL, where she researched plug and process loads, grid-friendly buildings, and automated fault detection and diagnostics. She also contributed to the development of the demand-side grid model, or DS-Grid. Subsequent to NREL, she researched community solar in Chile through the U.S. Student Fulbright program and worked for the Rocky Mountain Institute's Cities Renewables Accelerator team. Please welcome Amanda, and I'm going to turn it over to her to give her presentation.
Great, thank you very much for that introduction, Kim. You can go on to the next slide. As Kim said, my name is Amanda Farthing, and today I am going to be presenting on the energy consumption and usability of zero-client computing in office settings. And the data in this presentation are from a study conducted by myself, Rose Lagner, and Dr. Kim Trembath, who's leading this webinar, of NREL's Commercial Buildings Research Group. Next slide, please. So, why do we care about the energy usage of computers? Well, as most people on this call likely know, commercial buildings account for approximately 1/5 of the total energy consumption in the United States. And across all commercial buildings, computing loads constitute about 5% of whole building energy use, or about 1 quad per year. And this percentage of whole building energy use would be even higher if we were just considering office buildings, as Kim mentioned in her introduction of one of their recent studies. Therefore, wide-scale reduction in computing plug loads could offer significant energy and cost savings. Next slide. So in our study, we set out to evaluate the potential energy savings of virtual computing, which has been a quickly emerging trend in the computing space. You can think of virtual computing can take the form of cloud computing or storing your files in Google Drive and so on. But in this study, we focused specifically on comparing virtual computing using a zero-client device to traditional laptop computers in office settings. And so what is a zero-client device? It is that device shown on the left side of the slide. And as a formal definition, it is a small device with no local storage, memory, or processing ability. It connects to a personal desktop on a virtual machine that is hosted on a server, often located in a data center. So this entire infrastructure is called Virtual Desktop Infrastructure, or VDI. Next slide. And so in a typical workstation with a zero-client device, it might look like this. The zero-client device would connect to monitors, keyboard, mouse, and other accessories. And after plugging in a smart card, the zero-client would immediately open up your personal desktop on your monitors by connecting to a virtual machine. And again, that VM is hosted on data center servers and is accessed either via remote desktop protocol or personal computer over internet protocol. And once you have the setup with the virtual machine, you can access it either via your zero-client at your workstation with just monitors, or even on your own laptop or home computer, or in other conference rooms. Next slide. And again, it's important to note that the zero-client device itself is essentially a high-tech docking station, and the actual computing is happening elsewhere on servers often located in a data center that might look like this. So it's very important to consider the power draw on these servers when analyzing the energy consumption of zero-client computing as a whole. Next slide. So in our study, we asked 2 main research questions, the first of which was, can virtual computing using zero-client save energy? And the second was, when are virtual machines accessed by zero-clients appropriate in the workplace? Next slide. To address the first of these two research questions, we took a four-pronged approach. In the first, we directly submetered the power consumption of Xero clients and laptops at individual workstations. In the second, we calculated the power draw of virtual machines on data center servers. In the third, we analyzed whole building plug loads in NREL's Research Support Facility office building. And in the fourth, we administered a questionnaire to occupants of the building that inquired into their perceptions of both Xero client and traditional computing. Next slide. So as the first part of this study, we monitored 4 workstations, each of which used a Xero client device over the period of 1 week and a laptop device over the period of 1 week, and had similar setups in terms of monitors, laptop used, and accessories. And we directly submetered these 4 workstations over 2 weeks to determine the average power draw during the time when the computers were in use and were not in use. And throughout this presentation, I might refer to those times as occupied versus unoccupied hours. Next slide. So jumping straight to the results of that submetering, here we are looking at an overlay of all of the load profiles from this study for Xero client devices on the left and laptop workstations on the right. And on the left, I should have said Xero client workstations because we included the power draw of the monitors and keyboard and mouse as well. So unsurprisingly, due to the fact that laptops perform all computational tasks locally, the laptop workstations exhibit extremely varied power profiles throughout the day, dependent on the computational intensity of the task being performed. And conversely, the Xero client load profiles throughout the day is relatively constant. Looking further at these load profiles, we also noted that conventional laptops do have relatively good power management and can quickly enter low power mode if not in use, as you can see by the load profiles of the laptops going nearly down to 0 when not in use throughout the day. You can also note on the left that the Xero clients during unoccupied hours have 2 different low power modes, the first of which is idle and the second of which is being fully powered down. While there is no functional difference in those 2, they do have very different power consumptions. And so when using these devices, making sure that they're fully powered down, we realized was very important to overall energy consumption. Next slide. And can you go to the next slide quickly? Oh, yep, there it is. Okay, so sorry. As the second prong of our 4-step approach, we also calculated the average power draw of a virtual machine on the data center servers in NREL's Research Support Facility, or RSF. For this portion of the study, we considered the servers that are used for virtual machine computation and storage, and we also considered the power usage effectiveness of the data center, which accounts for the additional energy needed for things like cooling and lighting in the data center. So this amounted to a total average power demand of 21 watts per virtual machine on the data center servers, which was higher than we had expected. However, it is important to note that at the time of this study, the RSF was in the process of transitioning to new server infrastructure that was predicted to be much more efficient. And so these values are very dependent on the data center infrastructure in place. Next slide. So if we look at just the plug load power draw for each of the 4 users in this portion of the study, for all of the users except workstation number 2, the laptops, which are shown in red, had a slightly higher power draw than the Xero clients. Next slide. But if we consider now the 21 watt power draw of the virtual machine on the servers, then the total average power for zero client computing across all 4 workstations and across occupied and unoccupied hours was on average more than double that of laptop workstations. Next slide. So to corroborate these findings, we also analyzed whole building plug loads in NREL's RSF. And the RSF, or Research Support Facility, consists of 3 wings. Next slide. Titled A, B, and C. And this particular office building actually represented an ideal scenario for us to perform this analysis because, if you'll go to the next slide, in 2013, the C wing switched from using primarily laptops to 0 clients for all of their workstations. And so we were able to compare the plug load power per occupant before and after this transition, and also across present day A, B, and C wings to see if there was a difference in the overall plug load power consumption of an office space using primarily 0 client computers, or using primarily 0 client devices versus traditional laptop workstations. Next slide. And so after analyzing the plug load data, what we found is summed up here. So here we are looking at the C wing before and after that transition from laptops to 0 clients during occupied hours shown in the dark bars and unoccupied hours shown in the lighter bars. And a main finding here was that during occupied hours, the plug loads did greatly decrease after switching to 0 client computing from traditional computing. Next slide. And doing that same comparison across the 2016 C wing compared to the average of the A and B wing, the per occupant plug loads again were significantly lower during occupied hours in the wing that was using 0 clients compared to that using primarily laptop computers. Next slide. And so just to reiterate, here we're looking at just the plug load power draw in this C wing compared to the A and B wing across all hours. And this is per occupant. Next slide. But if we add in that VM server power consumption, that again was 21, we calculated to be 21 watts, then the C wing using 0 clients actually used 29% more power per occupant than the laptop using wings. Next slide. So now moving on to our second research question, which was, when are virtual machines accessed through 0 clients most appropriate? We distributed a questionnaire to RSF occupants that inquired into perceptions and preferences between these 2 computing types. We received nearly 200 responses, and of those who responded, about 20% used virtual machines as their primary computing system, 75% used laptops, and the remaining 5% used desktops. Next slide. And so our questionnaire results indicated varied preferences, unsurprisingly, but what we found was that the virtual machine technology at the time of this study was more appropriate for light and medium power users. So those users who are not constantly performing computationally intensive tasks, and that nearly half of the virtual machine users felt that their processing speeds were too low. And most of those who said the processing speeds were too low, again, were those power users. Our questionnaire also revealed that virtual machine users worried less about cybersecurity or theft of their computing systems while traveling, and that more virtual machine users than laptop users found it easy to access their files and applications from multiple locations. Next slide. And just to further iterate that dichotomy in responses, we have some fun quotes here. The first of which says, My virtual machine has changed my life. It allows me to do tasks from home that were impossible before. Another respondent said, I hate them. It's like torture trying to use a browser or Excel. And a third said, I love my Zero client and would give it up only with loud vocal disagreement. I hate having to lug things around like a tablet. Next slide. And so some key takeaways from the 4 portions of this study is that although Zero clients in the RSF did offer plug load savings, and particularly during occupied hours, the power consumption of virtual machines on data center servers can make Zero client computing more energy intensive overall. And so the virtual desktop infrastructure and data center efficiency are really critical in influencing the total energy consumption of this virtual computing paradigm. And we also found from our questionnaire that users perceived Zero clients to help improve their cybersecurity and remote file access, and that more work is needed to improve the usability and performance of Zero client computing if power users are a targeted user. Next slide. And some additional takeaways. A key portion of this study was analyzing the sub-meter building loads in the research support facility, which actually disaggregated to the extent of plug loads, to the extent that we could analyze plug loads individually. And so one point here is that while it may be an added cost, this sub-metering of building loads can enable very useful insights into opportunities for energy savings. The study also highlighted the role of user behavior in computing energy use. And so particularly during unoccupied hours, we noted that there could have been significant savings if, for instance, users fully powered down their Zero client device or laptop when not in use. And as an analog, there could be similar opportunities for savings through the use of advanced power strips and smart outlets to monitor those unoccupied hour plug loads. And next slide. If you're interested in viewing the data or learning more about this study, it can be found in Intelligent Buildings International. Next slide. And with that, I will conclude. Thank you for your time and attention, and we will take questions, I believe, at the end of this webinar if there's time. Thank you. I will now hand it back over to Kim.
Thank you, Amanda. And Amanda, that was a great presentation. Thank you very much for doing that. Very informative. If you have any questions for Amanda or me or the next presentation, please type it in to your question box, and we are going to compile those, and we will try to answer as many of them as we can at the end of this webinar. But if we don't get to them, we will send the answers out via email. So wonderful. Next, we're going to move on to the next presentation, and I have the pleasure of introducing Ms. Jennifer Amen. Ms. Amen is the Buildings Program Director at the American Council for an Energy Efficient Economy, or ACEEE. Since joining ACEEE in 1997, she has authored dozens of publications and articles on buildings and equipment efficiency technologies, policies, and programs. Ms. Amen leads content development for ACEEE's consumer-focused website, smarterhouse.org. Her current work focuses on maximizing energy savings from key buildings policies, including building codes and appliance standards, scaling up retrofit activity in homes and commercial buildings with an emphasis on deep retrofits and decarbonization, expanding opportunities for energy savings in low-income housing, and analyzing new opportunities for energy efficiency in the building sector. Now I would like to pass it over to Ms. Amen for her presentation.
Great, thank you so much, Kim, and thanks for the opportunity to present some of what we've learned through our experiences working on set-top box energy efficiency in particular, and a little bit more broadly on consumer electronics. If you want to move forward to the next slide, please. So what I'm going to do today is I'm going to focus primarily on our experience working with set-top boxes in the residential sector, what we've learned over the years working in that product category. And then I'll turn to additional product types that are related to set-top box energy use and some areas that we've identified for further research. So next slide. So the obligatory about ACEEE slide here. For those of you who aren't familiar with ACEEE, the main thing that I wanted to say was just that over the years, ACEEE and various of our partners, including the Appliance Standards Awareness Project and the Natural Resources Defense Council, have engaged in numerous negotiations with manufacturers and others to set minimum efficiency standards for a wide range of products. And those efforts are really what led us to our engagement with the pay TV providers in the cable, satellite, and telco industries on set-top box efficiency. Next slide, please. So traveling back in time to 2012, we really faced a dilemma. We had research that showed set-top boxes becoming a much bigger energy user in homes for a number of reasons. First off, were the wide range of expanded features that had been rolled out in recent years for set-top boxes, primarily the DVR, or digital video recorder, and the growth leading to the use of multiple DVRs per home. So we had many of the pay TV providers with their service offerings providing consumers or installing in consumer homes multiple DVRs. And so, there were some real concerns about that, and we started to look at the opportunity for standards in this area, since there were no standards at the state or federal level. And we also saw that there was very low participation in the Energy Star program, particularly for cable operators, even though cable accounted for the largest number of subscribers. So these were things that really got us focused on working in this area. So as you can see from the chart here, this was our estimate in 2012 of energy consumption for devices installed in homes. So we were looking at about 32 terawatt hours per year, and the potential for growth was quite staggering. When we did an analysis based on projections of where the industry saw the numbers for DVR installations in particular, we saw that there was the potential growth of about 50% to a total of 47 terawatt hours per year over the next decade if no other efforts were taken. So that got us all to come together. Next slide, please. So our talks with industry began kind of with two, we each had our own impetus bringing us to the table. So we had a lot of concerns about the energy use of set-top boxes, but we were also concerned about the legal authority to move forward with federal standards for this very, very unique product category. It's unique because the customers for the actual product manufacturers are the service providers that provide all the specifications for how these devices should be built. And then they're provided directly to consumers from those service providers. So it's not really a consumer product in the way that the standards rules are set out. So we were concerned that there may not be federal authority to do anything at the federal level. And so that was sort of balanced by a real concern on the industry side that there could be a patchwork of state standards put in place on their industry. And there were already signs that California was very interested in moving forward to address this issue. And the type of pressure that we were seeing from California wasn't just from the Energy Commission, but also letters from Senator Feinstein and others to the industry talking about their interest in reining in this growing energy consumption. So we really needed a regulatory alternative. And the idea was, is there a way we could approach a voluntary standard that would provide regulators with the certainty that they need that we would be capturing savings from virtually all sales or close to all sales of these products, but allow a little bit of flexibility for manufacturers to purchase products and test them out with new features that may at first not meet the energy requirements. So the way that we structured the agreement was that we needed to have the service provider signatories accounting for at least 85% of all pay TV subscribers. That was a way for us to ensure that all the biggest players came to the table. The industry had to work together to bring them all to the table, or we had an out as the advocates. And the advocates were ACEEE, NRDC, and ASAP. Then the agreement required that 90% of each service provider's newly purchased set-top boxes each year meet required energy levels. So in 2012, the manufacturers had come together on a voluntary agreement, and they had taken some initial steps to download new software to existing boxes. So we had seen a little bit of improvement in the legacy equipment in the field. So we decided to really focus on the new equipment when we joined onto the agreement in 2013. That was the first year. So the agreement set out these tiers for 2014 was at the Energy Star 3.0 level, but we negotiated a separate set of requirements to take effect in 2017. And then in 2017 and 2018, we regrouped and developed tier 3 standards and discussions for a pathway to tier 4. There were additional requirements set up for each provider type, cable, satellite, and telco, and these generally focused on requiring them to pursue whole home architecture designs, automatic power down, particularly for satellite boxes, which had particularly high standby power, and related topics. We agreed on using the ANSI CTA 2043 set-top box power measurement standard because there was no federal test method in place. And we agreed that there needed to be an independent administrator to publicly report the results each year. And other duties of the administrator were to do a random audit each year. So they're collecting all of the purchase orders and receipts from each of the pay TV providers participating. They would select one company to have an audit each year at random. And then we also established a process for remediation. And we have had to do several remediation efforts over the years, but in almost all of those cases, the service provider came forward. They knew they weren't going to meet their 90% requirement, and we were able to work out a pathway to capture those savings that had been lost. We also did field verification in the first few years in each provider's territory to go out and see if the products were actually performing in the field the way we were within the same range that they were tested in the labs. And we found very good agreement between those over the first several years. So with the new updated agreement that we signed in 2018, we've moved into a lab verification method. So all the details on the progress of the VA over time and the actual energy information on all of the models purchased since 2014 are available at this website, energyefficiency.us. So that's a great way to go and see all of what's happened over the years and how the progress has moved forward. Next slide, please. So in the first 6 years of the agreement, we saw national set-top box energy consumption decreasing almost 40%, even with significant improvements in functionality. That includes like expanded DVR capability, allowing recording of many more streams, for instance, the introduction of 3D, and now even moving into 4K and Ultra HD. Consumer savings of over $5 billion, 1.6 in 2018 alone. Significant carbon reductions, and the savings really exceeding the output of 4 coal run power plants. And so one of the things that I think is really valuable to show here, and one of the things that's been increasingly important to us is how can we make sure that we're capturing carbon savings as soon as possible through efficiency? Like, where do we have opportunities to get savings right away to help ease this huge challenge that we're facing and help us meet these goals that we've set out for carbon reduction over the next 20 to 30 years. So if we had gone a route with federal standards, by the time a federal test procedure had been adopted and the entire standards making process had rolled out, we would maybe just be seeing standards going into effect given the mandatory timelines in the next year or so. So these are all savings that really would have been lost, or on the other hand, we may have standards that don't really make sense for these products given all of the changes that we've seen in the industry over the last 6 years, and those standards would have been using outdated information as part of the policy making. So next slides, please. So just to give an example, here are some of the gains in efficiency that we've seen over the 6 years. So from before the VA to 2018, DVR average energy consumption is down by almost half. Thin clients down by about half. The non-DVR category, we see a smaller improvement, but those are becoming a less and less prevalent part of the set-top box mix out in the field. So I just put in some DVR and thin client to kind of show the difference in dimensions and to give an idea of what we're talking about out in the field. Next slide, please. So the agreement is really built around this approach, very similar to the Energy Star approach of establishing base allowances and then giving adders for different features. And so between the Tier 2 and the new Tier 3 allowances that will take effect for 2020 purchases, we see that across the board there are some, it looks a little weird, it looks like some increases in the base allowance, but that's because over time we've moved the advanced video processing decoder and high definition adders that were originally kind of added on top of a base allowance into the base allowance. So we have seen overall an improvement there. That's about 20 kilowatt hours per year in adders. And then just a couple of the adders that I wanted to point out. One is the cable card adder. And this is one I just wanted to point out and flag that as sort of an unintended consequence of policy making, where the FCC has required all cable boxes to include a cable card, which would allow them to work. So if you were a consumer, you could go buy a cable box and then you could say, oh, I don't like Comcast anymore. I'm going to go with Time Warner or whatever, and you could take that cable box with you. In reality, that never happened, but the companies still have to include this capability. So that is something that adds to energy consumption across the country, even though it's largely an unused feature. The newest things that we've added are access point, the 4K Ultra HD adder, high efficiency video processing, which is a compression capability, and telephony capability. So these are things that we've added over the years, sometimes through a process where a provider can bring to the group a new feature and we work out an adder for that. Next slide, please. So on the technology side, progress to date has really come from improved components, such as power supplies and the other pieces within the box. The architecture to allow unused components or features to go unpowered throughout the performance. Power management, sleep modes, and power scaling. We have seen more development on power management than the other categories. We're looking to get to more of a deep sleep mode performance and better power scaling with the introduction and availability of new 16 nanometer chipsets, which should accelerate the improvements in that area. This is an interesting example of where the industry had pointed out, we were looking at research on our end and saw that these new chipsets were available, and that we thought that would be a really great development for set-top boxes. But they weren't being offered for these products because it's been seen as sort of a niche, small part of the market. So the advocacy groups got together, and we wrote a letter directly to Broadcom asking them if they would please, work to develop and make available to the set-top box manufacturers this technology. and they are. So now we're starting to see, well, next year I think we'll see the first boxes that incorporate this technology for set-top boxes. The other ones are whole home solutions, so allowing homes to have one DVR and then use thin clients to access DVR content on all other televisions throughout the home. Cloud technology, another example of using virtual technology and relying on data centers. So a number of companies have introduced what they're calling cloud DVRs that don't require hard drives in the box. We're seeing a full shift to IP-based content delivery. So rather than having content delivered solely through the cable or satellite delivery, we're seeing all of the companies increasingly rely on IP-based delivery. And then we've also just seen a lot of improvements because at this point in time, virtually all of the pre-VA set-top box stock is out of the market. Next slide. So moving forward, the savings to come will come from, as I mentioned, improved deep sleep capabilities, better power scaling. We've seen a huge decline in overall set-top box purchases. So 23 million boxes overall in 2018, so cut in half from 2014 levels. DVRs alone have dropped in half last year relative to their sales in the 2013 to 16 timeframe, which is really the peak for DVRs. Continued move to IP delivery. And then as the companies increasingly have to compete with other streaming services and the many other options that consumers have in the market, we're seeing a shift to app-based devices, an app-based service that can speak directly to smart TVs, lower power over-the-top boxes like Roku and Apple TV, and mobile devices. And in fact, we're seeing many of the service providers either coming up with proprietary boxes that are very much like a Roku or Apple TV, or in some cases, providing their customers directly with a Roku or similar device that they can use. As part of this development, as of 2018, the set-top box providers, the pay TV providers, are required under the new version of the VA to report on the capability of the apps that they've made available, how many customers they're available to, and how customers are using those. Next slide. So I'm just going to switch gears and just briefly talk on a couple of related developments. The same service providers, along with other small network equipment manufacturers, have come together in their own VA. The advocates aren't a part of this, but I think they've seen some interesting results as of 2015 in reducing the average energy usage by equipment based on speed. So these are really efficiency improvements. We've seen little change in the actual power consumption per box, but a significant drop as speeds have gotten much faster over the last several years. For these three categories, broadband modem, internet integrated access device, and local network equipment, and these are becoming a more important part of the architecture of television viewing in homes where customers are using streaming devices and so forth. We're seeing that only the local network equipment sales increasing, the others are decreasing in sales overall, and the VA has led to a 20% improvement in efficiency in the first tier, and they have a second tier due to take effect in 2020 that'll give an additional 11% improvement. Unfortunately, there's no reporting on overall energy consumption or savings. I think that's one of the issues with not having the advocates involved in this agreement. But we feel we couldn't really be a regulator for two things. It's quite a heavy lift. Next slide. So the next thing that we've been looking at is smart speakers and video streaming devices to see if this is something we need to pay attention to, if this will be the next set-top box category. So NRDC released a report in August with some very interesting findings. Roughly 100 million of these devices are in use as of mid-2018, and I can only imagine how much more that is because this has been such a hot product category for the last year and a half. But that's roughly split between the two, slightly more smart speakers than video streaming devices. The smart speakers, the most popular ones on the market, we have here in the table, and you can see that they're pretty efficient. They have low standby use, despite the fact that they're constantly listening for users to call out and talk to them and tell them what to do. So we're looking at, though, about $100 million in energy consumption last year. Video streaming devices we found were also efficient, more efficient than set-top boxes. If you look at the range here, 11 to 24 kilowatt hours on average versus 35 to 100 for set-top boxes. And they use about 727 gigawatt hours last year, so just less than speakers. Some of the devices use significantly less standby power than others, so that's one opportunity that we see for products in both video streaming boxes and the speakers and the smaller devices that get plugged into the TVs directly. But one of the interesting findings was that linking smart speakers to TVs, and these were relatively new TVs, 2018 model TVs, could double energy use in some models and take standby from a half a watt to 20 watts. So we've been reaching out to the manufacturers to find out what their plans are for addressing this and making sure that the TVs can interface with these devices without experiencing this jump in standby. We also see that video streaming devices can increase TV consumption by doing things like overriding energy savings features, like automatic brightness control, for instance. So those are all things that there's a real opportunity to work with the manufacturers to come up with better solutions and also to educate consumers about these impacts. Next slide. So this is just an example, from the NRDC study. We saw, a potential increase of 142 kilowatt hours per year in TV energy consumption related to the use of a smart speaker. Next slide. So just to wrap up, I wanted to talk about a few of the research needs that we see. Similar to Amanda's study, consumers have certain expectations for this equipment, and these are really critical issues for service providers. The market is very, very competitive. It's evolving very fast. Subscribers have generally been fleeing these pay TV companies, so they're really looking for ways that they can continue to compete and offer competitive services. There are a lot of consumer expectations around functionality and wake-up time, for instance. One of the things that they've really pushed on, and I think why we haven't made as much progress in deep sleep, is that the resume time is something that, if it's over 30 seconds, it's deemed unacceptable to consumers. People want to turn on the TV and have that channel guide right there. But the interesting thing is people are pretty tolerant of a much longer lead time when they're going to turn on and then go to their Apple TV and maybe find the different options that they want to watch. So I think it'll be a mix of you're getting the technology right, but also making sure that we're tempering consumer expectations. There also needs to be a characterization of commercial sector end uses in this area and the potential for energy efficiency. Cable and satellite are widespread in hospitality, healthcare, and offices. There are specialty equipment types to deal with the unique features, so that they're small, so that there are security and privacy issues. The initial features, for instance, in a hotel for hotel billing and that kind of thing that they include in the system. And it's also interesting to learn more about what the impact of new streaming options will be and how rapidly those options might be adopted in the commercial sector. We're seeing some of it in hotels, but I'm not sure. I know as I've been traveling, I've seen a lot more hotels that allow me to sign into my apps directly on the TV, but I'm not sure that that's being offset, that's offsetting this other energy use. And then finally, upstream energy use associated with these pay TV services and video streaming and the projected changes that we see as set-top box use declines. So this is everything from head-end equipment and the energy used in data centers to uncovering some unanticipated issues, like one that we've discovered in working with the cable and satellite industry, and that is that there's been a legal issue where many of the many of their agreements with the content providers, so the movie studios and so forth, have required them to maintain a digital copy of every movie downloaded by a consumer. So if you have 1 million consumers downloading Spider-Man Homecoming, for instance, there would be 1 million copies, digital copies out there on that service provider's data center space. So that's something that we see as a real potential waste of computing resources as well as energy. And there's some work going on now to see how this type of agreement can be changed in the future to deal with the really changing way that people are consuming video materials. Next slide. So that's all I have today. Thank you so much for your attention, and I look forward to any questions.
Thank you very much, Jennifer. That was extremely interesting, and also kind of refreshing on how an organization can really impact the energy use for devices from a specific industry. So both of these presentations focus on devices that impact our plug load energy use, and both of them include solutions and future work associated with improving plug load energy use. And so we were happy to showcase that here today. I have a few more minutes left, and I want to hit a couple questions, one for the Zero client and one for the voluntary agreement set-top box presentation. And so the first one that's directed for Ms. Farthing with the Zero client is, what specific areas should the market focus on to improve performance of Zero client computing?
Great, thanks for that question, Kim. So on the energy side, if I'm interpreting that question as energy performance, we really saw that there were two almost equally as important prongs in the energy consumption of the Zero client computing setup. The average power draw of just the Zero client workstation was about 20 watts, and the Zero client, the virtual machine on the servers, was about 21 watts. And so really focusing on the virtual desktop infrastructure technologies can lead to huge improvements in terms of energy performance. And some of the areas of focus there are virtualization or dynamic allocation of virtual machines on servers. And just as an example, when I mentioned that the RSF was considering or was in the process of transitioning to improved server infrastructure, the power draw that we estimated of a virtual machine on one of the Blade servers that would be used specifically for virtual machine computation would have been about 1/3 of the power draw that we saw in this study. So there's really huge areas for improvement there in terms of virtual desktop infrastructure, technology advancement, as well as improvements in data center efficiency overall. Although the power usage effectiveness of the RSF data centers was about 1.16, so really good. Other data centers might need to look into similar efficiency improvements such as hot aisle containment or lowering temperature set points, etc. And then just quickly on the workstation side, that idle power mode was really an area to focus on for energy performance.
Great, thanks, Amanda. And then real quick, I have one more question for Jen. What other device manufacturers does ACEEE work with to reduce energy consumption and plug loads? Is this voluntary agreement model replicable to other plug load devices?
All right, thanks. Yeah, I wanted to be sure and get to this question. I think it's an interesting one. So we really work across the industry. I think anyone who has plug load energy using devices, we're interested in working with. Although we'd really like to work with them through some of the more long established programs, whether it be Energy Star, looking for opportunities to work with utilities or other market players, or whether the traditional standards approach makes sense. I have, I think, a number of concerns about the replicability of the VA approach relative to standards and Energy Star and so forth. We moved forward with this product simply because it's very unique. Some of the issues that I had brought up about, not really being a consumer product out in the marketplace, for instance. And so we didn't really see a pathway for standards necessarily for this product. So we decided to go the VA route, and it has been, while it's been a really successful experience, I think we've really met our goals, and we were able to accelerate those energy savings. It's really not a sustainable model given the amount of time and resources that the advocates have had to devote to the process to make sure that we've seen the results that we want to see, to make sure that the process is credible, that the regulators feel confident that the process is moving forward and that we're getting savings like we would through a standards process. So it's kind of a lot to put on outside players to kind of play that regulatory role. What I'd like to see instead, and what I think might be a more promising pathway, is for us to work on changes to the standards process that would allow for more rapid adoption of standards for products like these that have a much shorter design cycle and a much shorter life cycle than other products. That's really, I think, the main, when the standards program was originally set up, it was dealing with products that had much longer lifetimes, the major plug loads in homes, appliances, and so forth. So we see some, really large time frames that don't accommodate this equipment well. But we do see, like, the California Energy Commission is able to move forward with standards on these types of products in a much shorter time frame. So we'd like to see how we might be able to make improvements to the federal appliance program that would allow us to get standards activity in a much more timely and responsive fashion for these types of products.
Great. Thanks, Jen. And thanks, everyone, for staying on a little bit longer. I want to thank you guys for attending this call. We're at our time. And if you have any more questions, please feel free to email us, and we are going to send out responses to the questions that didn't get answered in this call later today. So thank you all.